In this video, we're going to learn some matrix algebra. I'll explain what that is through this example. So the matrix M has eigenvector values lambda equals 6 and minus 1, and here's M. Okay, given that A, some new matrix A, is M plus 3 times the identity, find the eigenvalues of A. Well, I'm going to show you a shortcut for this, but let's do it the long way just for now. So what is A? A is M plus 3i, so I'm adding 3 to the diagonal. So that's 7, 2, 5, and then 4 here. So finding the eigenvalues of that involves finding the determinant of this matrix and setting it equal to 0. So that's giving me 7 minus lambda times 4 minus lambda minus 10. So that's lambda squared minus 11 lambda plus 28 minus 10, that's plus 18. Okay, this factorizes, it's lambda minus 2 and lambda minus 9. Okay, so the answers are lambda equals 9 and 2. So what's the connection between those and these? Well, look, these are just 3 bigger. And where's that come from? Well, no surprise that it's the 3i here. It's adding 3 times the identity. So why is that? Well, let's think about this from the definition. If we do m plus 3i multiplied by, well, let's multiply it by the eigenvectors of M. So let's say that the eigenvector or an eigenvector of M is E. Well, what is this? I can expand this and I can get M of E plus 3I of E. Well, by definition, M of E is just lambda E. Remember, E is the eigenvector of M. So that's just lambda times E. And 3i times E, well, I of E is just E, so that's plus 3E. And so what do we get? We get lambda plus 3 lots of E. So what have I just discovered? I've just discovered that if I take this matrix here, all that matrix does is scales this eigenvector by lambda plus 3. So this tells me 2 really interesting things. It tells me that if I take a matrix and add any amount of the identity, that the resulting matrix I get will have the same eigenvector, but its eigenvalues will just be 3 bigger. So that is why the eigenvalues of this matrix were 3 bigger than the eigenvalues up here, but it will actually share the same eigenvectors. Now, there are a few principles which we're going to learn now, and each one we can prove, and these are results we can use in interesting ways. So here's the first result. If matrix A has eigenvalue lambda and eigenvector E, and matrix B has eigenvalue mu and eigenvector E, so the same eigenvector, then A plus B has eigenvalue lambda plus mu and eigenvector E. Now that looks like so much jargon, but let's go through the algebra and then look at a very, very simple example. So if we were to take the matrix A plus B and apply it to this vector E, which we know is an eigenvalue of A and B, and we expand this, we get A of E plus B of E. But since E is an eigenvector of A with eigenvalue lambda, A of E is lambda E. And since E is an eigenvector of B and mu is the corresponding eigenvalue, B of E is the same as mu E. Factorizing out E, we get lambda plus mu times E. What does this tell me? This tells me that applying the matrix A plus B to E is the same as scaling it by lambda plus mu. That means that lambda plus mu is the eigenvalue for the eigenvector E for this matrix. So what does this mean in practice? It's super simple. It means if you have two matrices that have the same eigenvector, then when you add them together, they'll still have the same eigenvector, but your new eigenvalue is just the old eigenvalues added together. So here's another principle. If matrix A has eigenvalue lambda and eigenvector E, and B has a different eigenvalue but the same eigenvector E, then AB, that is like the composition of A and B, has eigenvalue lambda mu and the same eigenvalue. So again, this is very easy to prove. This is saying work out A times B and apply that to E. Okay, now one nice fact about matrix multiplication is that it is associative. There's a lot of jargon here, but matrix multiplication, it is associative, it is distributive, but it's not commutative. Now, what does that mean? It means that you can, that A, B, and then you can multiply A times B first and then apply it to C, and that's the same as first applying B to C and then applying A. I mean, addition is associative, because if you're working out 1 plus 2 plus 5, you can do the 1 plus 2 first and then add 5, or you can do the 2 plus 5 first and then add 1. It is distributive, which basically means you can expand brackets, that if you're doing A of B plus C, that's the same as AB plus AC. So multiplication is distributive because 2 times 3 plus 1 is the same as 2 times 3 plus 2 times 1, but it's not commutative. So with matrices in general, AB is not the same as B times A. Of course, numbers are commutative if you're adding or multiplying. So jargon, 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 what does it mean? It means that this, you can either work out AB first, or you can do B of E first. So A times B of E. Now, what is B of E? Well, E is an eigenvector of B with eigenvalue mu. So that's A times mu E. Remember, by definition, since E is the eigenvector of B with an eigenvalue of mu, B of E is mu E. Now that's just a constant, so we can pull that out. Mu A of E. And then what is A of E? Well, again, by definition, the eigenvalue for A, for eigenvector E, is lambda. So A of E is lambda E. So that's mu times lambda E. And what have we found? We've just discovered that applying the matrix AB to E is the same as multiplying it by mu times lambda, or lambda times mu, and therefore lambda times mu is the eigenvalue for the matrix AB. Okay, this all seems very, very abstract, but basically what we've shown is that if you've got two matrices with the same eigenvector but different eigenvalues, then if you add the matrices, you can add the eigenvectors, the eigenvalues, and if you multiply the matrices, you can multiply the eigenvalues, and the eigenvectors stay the same. And we can use this to solve some cool problems. For instance, let's try to find the eigenvalues and corresponding eigenvectors of a to the 5, where a is that. Well, that sounds like it's going to be an awful lot of matrix multiplication, and I can't really be bothered to multiply a up 5 times. However, we don't need to, and we can use the result we've shown. A to the 5 is just a times a times a times a times a. Now what that means, according to our previous result, is that if we know the eigenvector of a, it has an eigenvalue, then the eigenvalue of a to the 5 will just be the eigenvalue of a raised to the power of 5, and it'll have the same eigenvector. Let's just work through that now. So let's find the eigenvalues and eigenvectors of this matrix. So that's 3 minus lambda, 4 minus lambda, minus 0, that's convenient, equals 0. So our lambda 1 is 3, and our lambda 2 is 4. And now we can find the corresponding eigenvectors, because 3 minus 2, 0, 4, applied to x, y needs to be, by definition, lambda x and lambda y. So we get, let's maybe start here because I think I can jump straight to it. 4 times y should be, let's take 3 first, 3y. Okay, well, that implies that y is 0. Okay, running across the top row, we get 3x minus 2 times y, which is 0, should equal, when lambda is 3, 3x, which means that x can be anything. So let's say x equals 1. So when lambda equals 3, our first eigenvector is just x equals 1, y equals 0. If we do the same thing now, when lambda is 4, that second row gives me 4y equals 4y. So it's y that can be anything. So let's go with y equals 1, let's say. And now this top row gives me 3x minus 2 times y, so it's minus 2, should equal lambda x, which is 4x. So subtracting 3x on both sides, we get minus 2 equals x, and there's x. So that means that when lambda 2 is 4, our second eigenvector is x equals minus 2, y equals 1. So here are my two eigenvalues and eigenvectors. What does that mean for A5? Well, it means that the eigenvalues of a to the 5 are just 3 to the 5 and 4 to the 5, but it will have the same eigenvalue. It must have the same eigenvalue because I know that a to the 5 of some eigenvector e is just, well, it's a to the 4 times a of e, which is a to the 4 of lambda e. And then I do it again and again and again and again until I get lambda to the 5 e. So my first eigenvalue of this is 3 to the 5, and if I know my powers of 3, that's 243, with corresponding eigenvector unchanged. And I just need to do 4 to the power of 5, which, if I know my powers of 2, is that. And that has the same eigenvector as well. It's minus 2, 1. So that principle, that multiplying a stack of matrices with the same eigenvector doesn't change the eigenvector, but just multiplies up the eigenvalue, can turn what would be a really complicated problem into a relatively straight, not easy, but relatively straightforward one. Okay, so that's a little intro to matrix algebra. We're going to continue exploring this in the next video, so see you there.